Thank you for your kind introduction. And as you might have heard about it, that I started my career in civil engineering, and then I did my masters in mechanical engineering, and then I did my PhD in aerospace engineering, and in between I was in jobs in electrical manufacturing company. Okay. So, I am basically jack of some of the trades. Okay. I wouldn't say I have mastered anything so far, but I am really enjoying my life in terms of whatever knowledge comes in front of me, grabbing it and try to apply it. Of course, application of the knowledge is very, very important, otherwise that knowledge would not be of any use to us. So, I will just start with this presentation today, that is smart materials for sensing and actuation. Now, generally when I begin with this, I should also explain what is the connectivity of this with the theme of the tech week, that is introduction to robotics. Now, as you know that a robotic system has to have some sensors and some actuators. Okay? Otherwise, how would it perform? It is not just the brain, it is not just the AI, okay? But it has to have some actuators to move, to do something, to do some work, and it has to have some sensors to pick up that what it is doing, whether it is doing correctly or not, to rectify itself. Okay? Towards that direction, one of the challenges in many robotic system is actually gripping. Just last month, we had a IITK team which finished in Amazon with a podium finish, and what Dr. Lakshidhar Behra told me is that, you know, if only we had a good gripper, we would have been the champion of the competition. Okay? So, good gripping is always a challenge. Ashish and I am working on IPMC based grippers, because this is a polymer which deforms a lot, like this particular deformation. It deforms a lot, and hence it can be used in terms of gripping of the system. And one of the student of Ashish had actually used it in a SCARA robot. He is based on that CMERI Durgapur. Okay. So, it is possible to implement such a system. Now, be it IPMC or be it any other system, it is essentially in the domain of smart materials. So, until and unless we know the power of these materials in terms of sensing or actuation, we will not be able to make a very high quality gripper. This very picture, the cover photo, is from Purdue University, where Dr. Manuel is actually using this in terms of pollution or pollutant, very micro pollutant gripping from water. Okay. So, for that purpose, you know, this particular system is very good, and you will be surprised that it is very low cost, as it is made from micro machining of simple sellotapes that we use in day to day process. Okay. There is a hi-fi name of it, but it is nothing but a sellotape. So, in our talk today, we will talk about the application of smart material first. We will talk about smart systems that we can develop using smart materials, smart actuators. There are some direct and reverse effects. There is something called artificial muscle, and that is based on shape memory material. So, hence I will deal quite a bit with this material. And finally, this is something of my current interest, that once we develop a system, how about if it gets damaged in between? Okay? The robot is supposed to be automatic on its own. It is an, you know, it is one of the best outcome of an automated design. So, if it is automatic, then a system, then of course, it should be able to take care of its health as well. Okay. So, can it heal itself? So, that is what is the self healing part of it, which is also based on some smart material. So, this is what is my long wish to cover in this talk. Now, in terms of applications, the smart materials are used in vibration and chatter control. They are used in shape control. They are used for micro positioning devices, distributed sensing. So, vibration and chatter control is, the name itself is very clear. to you. Chatter particularly is a very special form of vibration which comes for tool, for the tools, okay, in the machining process, and you can control that. We have one of the imprint project where we are working on this using smart material. Shape control, there are many uses. I will show you one of the uses that we are working on. Micro positioning once again is related to the assembly process. Very fine assembly process tuning can be done using this material, best actuators and sensors. Distributed sensing is something which is very interesting, because it is like a kind of a biomimetic of whatever we develop in terms of say fingers, okay, or haptic systems. Now, the reason why it is important is that this happened, we were working on Da Vinci robot. Okay. There was a project, it is a DST Indo-Italian project in which Ashish and I was working together, and our goal was to develop a slave finger. Okay. This is a master slave configuration which can carry out a high precision surgical activity. Okay. So, here is a surgeon who is putting his hand on the gloves, okay, and his finger movement is actually getting recorded, and the slave fingers have to carry out the same work whatever the surgeon is doing. Now, the trouble is that in usual sensing system, it is like 3 or 4 sensors like joint rotations per finger, where you put small MEMS based accelerometer and you sense it. But that was not able to capture what a surgeon actually carry out in terms of a surgery, precisely because there are much more than just joint angle rotations in a surgeon's finger. It is like an artist's finger, you see. So, it has finite control of each one of the muscles. Okay. So, you have to know, rather instead of pointed sensing or pointed actuation system, you have to know how each one of these finger distributedly, how this actually deforms every time when you are carrying out an activity. So, you need a distributed sensing system to do it, and that you can only do with the help of smart materials. I will show you. And this last one finally is actually for energy harvesting. So, this is because these materials are transducers in nature. Transducers means they have a coupling between mechanical and electrical field and vice versa. So, they can convert mechanical energy to electrical energy, and since they do that, then if there is an environment where lot of vibrations or motions are happening, you can actually extract some part of the mechanical energy and use it for charging your sensor networks. That actually helps in terms of energy sustainability of the system. So, this is our active vibration control. Many of the good quality cars today comes up with the suspension systems which are having a particular fluid in it, and that fluid actually changes its viscosity when it is subjected to magnetic field. We call this fluid as magnetorheological fluids. So, based on whatever is the road condition, and as you know, in our country the road condition varies a lot. So, based on the road condition, you can actually change this shocker in terms of a very soft to a very stiff shocker, so that it can absorb the undulations in the road by changing the viscoelastic property of the system. So, that is one application of the smart material. This one I showed you that this is a laser micro machined magnetically functionalized hygroscopic bilayer, and which is nothing but a sellotape type of a system which is machined, and these are actually polymers which when you subject it to a small voltage, they are actually hygroscopic. There is a large scale moisture transfer takes place between the cathode and the anode depending on the material. So, that is why this large deformation is possible in such a system. This is in fact also true for IPMC based systems that we work on, that there is a large scale of transfer of moistures, okay, in the cationic transfer of moistures that takes place, and hence the bending happens to the system. The only thing is that this phenomena is quite slow. So, there is a time related issue with it, and hence that has to be accounted for while designing the system. But talking about a fast system, this is a fast system already in the market. This is a XYZ piezo stage. There are various companies, Micro Epsilon is one of the company, or PI, they actually supply it, and it gives you sub-nanometer resolution. No mechanical actuator can give you this kind of accuracy. 200 micrometer travel range, extremely fast step, and settle in 5 millisecond. That is the good part of these devices. Energy harvesting, I am just showing one application which is already there, and that is related to the engines, which has a very high temperature. So, you have a thermoelectric energy harvesting capability, which can extract the energy from a engine, aircraft engine for example, and then use that in terms of development of in terms of powering the sensors. So, what gives this beautiful power to the smart materials? Well, if we actually categorize it in terms of input and output, as you can see that you have various inputs here that you can give to a material, electric input, magnetic input, mechanical input like stress, heat or light. And in terms of output, you can measure either the current or charge, you can measure the magnetization, the deformation, strain, temperature or the light intensity. Now, if you take this as the matrix, then the diagonal part of the matrix is something which happens in every other material. There is no smartness in it. For example, if you apply electric field, some materials will be conductive, so it will pass the charge. Some materials are dielectric, so it is the permittivity or similar dielectric properties which comes into the picture. If you apply magnetic field, materials will show magnetization. If it is having the magnetic property, if it is not diamagnetics etc., it will not show, but it is the diagonal property only. However, imagine that using electric field you are finding deformation happening in a system. That is a cross diagonal term, and that is called reverse piezoelectric effect, and that is used for piezoelectric actuators that I have just shown. Similarly, using magnetic field, if you see a deformation in a magnet, that is called Joule effect of magnetostriction, that we use for magnetostrictive system. For heat, there is the shape memory alloy that I will show you, which is also called muscle wear. For light, it is photostriction, and this is as far as these inputs are concerned from the deformation point of view. Now, if I give mechanical force, then if I see there is a change in current, then this is something that I can use it for smart sensor, or if I see a change in magnetization in a material, that is called Villari effect, I can use it as a sensor. If I see there is a change in temperature, I can use it as a sensor. If it is a photoelastic effect, I can use it as a sensor. So, this horizontal line, except this diagonal term once again, that force produces deformation, stress versus strain is elastic modulus governed thing, there is nothing new in it. Every material exhibits that. But this 1, 2, 3, 4 can be used as sensor in the row, and in the column this 1, 2, 3, 4 can be used as actuators. Right. So, this point we have to keep in our mind, that these are the basic phenomena we are attacking. Okay. Look at it the other way. I have an electric field available with me. How many types of smart material based actuator I can build? I can build a piezoelectric smart actuator. I can build a electrostatic MEMS based actuator. I can build a electrorheological fluid based actuator directly with the electric field. If I consider this electric field in a variable coil solenoid through a magnetic field, then I can even extend it to magnetostrictive or to magnetorheological fluid. Now, let us say I do not have either electric or magnetic field, I have a chemical field. Okay, then we have to use the mechanochemical actuators which reacts to chemical changes. I will show you some examples. Let us say none of these things are available, only heat. Well, then you have to use shape memory alloy based systems which are either metallic alloys or polymers. If none of them are available, yet I have to do some change, use light. There are photorestrictive actuators which today respond nicely to the change in the light intensity. Basically, between UV light and visible light, if you can constantly change, you can work with it as an actuator. What is the level of actuation possible from such a system? Okay. So, that for some of the system that is readily available like piezo ceramic, you get a free strain of 2000 micron. How much is 2000 micron? What is the thickness of your hair? Can somebody tell me? Huh? How much micron? The micron level is correct. How much you said? Yeah, it is not so small, it is around 50 to 100, in that range, it varies. So, hair thickness is let us say 100 micron and this is 2000, which means it is basically 20 times that. Okay. So, you can imagine how small is this deflection, it is not much. Okay. Now, naturally you do not it does not happen except that if you use a nickel titanium alloy, which I will show you, where it is clearly visible. None of these you will be able to see with your eye only visually that the deformation is happening, but yet they are useful. Why they are useful? Because if you try to stop this deformation, they actually generate the force, and it is that force that we actually use in terms of pulling of a mechanical system. So, that is how we apply the trick. Secondly, in terms of modulus of elasticity, piezo ceramics about 60 to 70 GPa, quite good. Aluminum is about 70 gigapascal, magnetostrictive about 48 GPa. Okay. This material nickel titanium alloy, it is a shape memory material, it actually has two different modulus of elasticity. In a low temperature it is about 30. So, it is flexible in low temperature. In high temperature it is about 90. So, it is very, very stiff in the high temperature. So, it is good. FSMA is not very good, but I doubt this data, it is actually 45 to 82, that decimal we have to remove it. 45 to 82, it is not so small. Now, this one PVDF is piezoelectric in nature. This is actually polyvinyl difluoride. This has a low Young's modulus, only 2 to 3 gigapascal like any polymer. But the good part is that because it is flexible, so you can give it a shape. So, suppose you are trying to bend those fingers once again, these things are pretty rigid in nature. So, you cannot directly use them, whereas this one you can directly use to actually give it a shape. So, that point of view it is quite good. Next important point that comes for our analysis is the bandwidth. Bandwidth actually tells us how fast you can work on a system. If the bandwidth is high, like piezo ceramic has up to gigahertz bandwidth of piezoelectric materials, which means it is very, very fast. And then this is slightly lower than that, magnetostrictive material, and on the other hand these materials are quite slow, 0 to 10 hertz. So, it takes time for them to actually respond dynamically. So, that is what actually is important for us in terms of determining which material or selecting a material. Now, why we will be interested? Okay? Here is a comparison. You have pneumatic pressure, hydraulic pressure, electricity, and the last groups are the smart materials. Now, you have various options in front of you, motor or cylinder or servos, DC servos or AC servo or linear stepper, voice coil. If you look at them, their accuracy and this accuracies, many of these smart materials have actually better accuracy. So, they are good from the accuracy point of view, but their displacement is low. You get a larger displacements from pneumatic and oil pressure and electricity systems. So, you have to have a technique of using this low displacement, as I told you, blocking that, getting the force, and then use a mechanical system to deform. So, that technique if you use, you can retain this accuracy, which is fantastic, and also you can retain the response time, which if you see here, it is quite slow in comparison to the second in milliseconds. It is almost going towards the microsecond range. So, it is very fast if you can develop such a system. So, there are three reasons why we use this new domain of actuators wherever we get a chance. A is that it is highly accurate, and B is that it is very fast, and C, which is very important, I did not show it here, they are very, very lightweight. Okay. So, the motor assembly is very heavy. So, you cannot use it. Okay. I am developing currently an exo-leg system. Exo-leg is something like which helps, if you wear it, it helps a person to walk. Okay. So, you have to have some degrees of freedom to simulate on it. You have to have a hip joint simulator. So, it has to develop a motion like hip joint motion, and similarly the knees and also the feet part of it. Now, this if you try to use a conventional motor system, then each one of them comes of an weight penalty of something like 1.5 kg, the type of force and motion you have to generate. So, naturally, you imagine that something you are wearing which is something like a 15 to 20 kg system, it is too heavy. On the other hand, if I can use the shape memory alloy wear based muscle wears, I can reduce the weight by about 1/10. So, it becomes actually much more wearable actually as a solution. So, that is why tomorrow's solutions will actually come based on this type of smart materials. Now, a little more that in any smart material, there are two things that can happen. One is called a direct effect, another is called a reverse effect. The direct effect talks about if I give an input as a mechanical force or stress, and if I take the output as a electric field or magnetic field change. So, naturally, this is used as sensor. Okay. On the other hand, if I give an input stimulus which can be electric, magnetic or thermal, and I get output as a strain or force, if I stop the strain I get a force, then it is called the reverse effect, and that is used for actuator development. So, the good part is that there are many smart materials self sensing, that means they have both direct as well as the reverse effect. So, they can be used for both sensor as well as actuator, that is the good part of it. This was the stair climbing Titan 6 group of robots. From there the ACM R5 snake like one, and from there the bipedal robot M2. If you look at the evolution of such systems, you would see that it is actually in terms of motor based rigid links that is there basically in all of them, and gradually we have been able to reduce the number of motors, the load, the power of motors, etc. From there we come to muscle based actuators. The very first groups are called PAMs, pneumatic artificial muscles, and then from PAM we come to systems like IPMCs or smart materials, which does not even need it. See, one of the problem of the muscle based pneumatic system is that you always need a supply of compressed air. So, it makes it very bulky. On the other hand, if you use this type of material, this is used in Mars actually by robot pathfinder, and you can use a simple electrical voltage to generate a direct single link manipulator, or you can generate, we have shown in one of our paper, you can generate a 4-bar mechanism also using this type of a system, and that can be a much more portable type of an actuator. But so the drive from your rigid actuator to more flexible actuator, that is what is happening today. Now, I will show you some smart puzzles based on shape memory alloys and electroactive polymers. So, before that we have to talk about that what is shape memory effect. There are two common effects, one is called one-way effect and another is called two-way effect. In the case of one-way effect, the material always remembers one shape, that is the parent shape, that is in the austenite phase of the shape. In case of two-way, it actually remembers both austenite phase as well as martensite phase. If you recall from my earlier slide, this is a low temperature state and this is a high temperature state. This is a more flexible state, this is a less flexible or a high stiffness state. So, if a material can have two memory, it is even better than one memory. Can a material have more than two? Yes, there are some polymers now which can have 3 or as well as 4 memory states. So, the more number of memories that a single material can retain, you can reconfigure it using that for so many number of times. So, that is advantageous for you. Now, if I look at the curves, so if I apply temperature, and as you can see here that with the temperature you are starting the austenite start. So, you have to look at it the heating part of it first. As you heat it up, it goes to austenite complete. So, it gives you full austenite situation, and as I reduce the temperature, it goes to martensite start and martensite finish. There will be always an hysteresis involved in it. That means, the heat that you are giving for the phase transformation, a part of that heat is actually lost in the dissipation of the system. So, you will not be able to follow exactly the same line. If you look at it from the crystal structure point of view, what happens in a shape memory material, we can start from somewhere here at the cool stage, and it can be at a twinned martensite stage, where each layer is actually a mirror reflection of the earlier layer. So, there is this line and then there is a mirror reflection, and that is how it is happening. So, it is just like folds. Now, that means it is deformable. So, you can deform it, it will go to detwined martensite phase. If you apply heat, it will go to the high temperature state, which is the austenite state, a very stiff state. If you reduce the temperature, it will come down and it will come to the twined martensite state. So, for one-way shape memory effect, it always remembers the shape at the austenite level. For two-way, it remembers the shape at austenite level as well as it remembers the shape at the twinned or detwined martensite level. This is how a typical one-way effect will happen. You take a shape memory material, you apply force. So, from linear domain gradually there will be a plastic deformation and there is no change of temperature. So, it will plastically deform until and unless it goes towards failure. Let us say I am not increasing the load beyond a certain point that it fails, I simply unload the system. It comes down to 0.3 where it shows the level of plastic strain that is retained in the system. It will be there until and unless you actually heat it up. If you heat it up, this plastic strain will completely go away, it will recover and it will come to 0.4 where there is no deformation in the system. And then if you cool it, you can go to stage 4 to stage 1 with any further change in the system. So, the trick is that if I have a structure which is detwined here and I go through the heating cycle, I can come to 4 where it will not be detwined anymore and it will have the memory that you have trained it to retain. That is the one way shape memory effect. Of course, there is another effect that you will see in such material, which is called pseudo elasticity, where you do not come to the interim twine martensite phase, but simply at the austenite high temperature phase, by using loading and unloading, you can shift between austenite to detwine martensite. This is used mostly for vibration control, because there is a large hysteresis that is there present in the system. The materials that shows this effect: silver cadmium alloy first, and then copper zinc aluminum, copper aluminum nickel, and nickel titanium. Mostly you will get the last one from market, it is known as nitinol. That NOL is for Naval Ordnance Laboratory, who have actually discovered this material. And you can use it for various type of purposes, like as you see here, control of aerodynamic surface, for vibration isolation, for grasping by robotic fingers you can use it, space exploration, filters and solar array hinges. There are various applications that is possible with it. This is one that my students have developed. It is called a reconfigurable system. The idea here is that instead of having one single robot, you develop small autonomous robots, and whenever there is a reason to actually do a work that one single robot cannot do, then you actually join all of them together. So, as you can see it here, that you can see it here that there are each individual modules, and they have their own sensors, and they can actually track whether there is another one. So, they have indicated that yes, let us join together, and so they are joining together to form a new one which is slightly bigger in nature. What is the advantage of such a system? Well, if I look at the next one, you will see that if they join, what is the advantage for them? They have an obstacle which individually they cannot actually tackle. So, by joining this, they are able to change, they are able to actually cross this obstacle. As you can see, each one of them comes with a facility to get joined with the next one, and this locking is done with the help of shape memory system, because it has a memory that how to join. So, every time you have to do this, and this we have a patent actually to develop such reconfigurable systems. So, suppose the idea is that you can use it for example for smoke sensing against firefighting. So, you have many reconfigurable robots roaming all around. Somewhere they sensed a gas, then they immediately go to the firefighting system, and there they assemble, they lock themselves. So, they have more payload carrying capacity, they take the firefighting instrument, go back, and then they apply it. So, that is the idea. In a distributed manner, you carry out reconnaissance, and then you join together in order to carry out a function. We have used a very similar technology, I will not show you here, because now we are going to use it for all the riverine system here in the northern part, all the big 5 rivers. So, we have used it in terms of what you call pond cleaning robot. Okay. If you see it in my side, there is a very popular robotic system, and here also you can have multiple robots which first looks at that what is the water floating object, and once they see that, then they actually call other robots, form a chain, and then they extract all the things together. So, that is the advantage of a reconfigurable system, and you can dynamically allot that I need 10 robots here, 20 robots here, or 5 robots there, you can dynamically allot that thing. Now, talking about strategy is easy, but designing is not at all easy. If you look at the constitutive relationship itself, it is quite complicated. You have the stress in one side, you have the strain, that is the first part of the elastic matrix, then you have the pre-strain, then you have something which is the phase transformation. The zeta s and zeta s0 all are related to how much of austenite transformation has happened to the system. And the last part is something which is related to simple thermal expansion. So, a shape memory material, in order to know that how much of force you are going to get every time, you have to actually solve this puzzle, because you have to know how much of strain has happened, you have to know how much of material got changed to austenite level, and then what is the thermal expansion coefficient. Considering all of them together, you will be able to find out what is the stress level or what is the force that you can get from the system. Now, for simple wires, to calculate the xi s is very difficult. So, there is a Brinson model that we use, and it talks about reverse transformation. From martensite to austenite you have one set, and for austenite to martensite you have another set for forward transformation. So, it is very difficult to do it online, hence in certain cases we actually use an equivalent coefficient of thermal expansion model, and it is very simple, like you already know the thermal expansion coefficient of a system. All we have to know is, for the shape memory based system, from the experiments we find out that what is the response of the system, and then find out what is the equivalent thermal expansion coefficient which can actually, which has accommodated this forward and reverse transformation for both cooling and heating, this alpha changes, and once you know that alpha experimentally, you feed it up, the model becomes simpler. Only thing is that you have to carry out a series of experiments to have this simpler model. I will show you a muscle SMA based trajectory tracking system that I have developed, and which I hope that I should be able to change it at a later stage for actually master slave actuation system. What you see here is that, like your two muscles, biceps and triceps combination, it is a tooling system, and these things are getting heated. These are the shape memory alloy wires, and I told you that you can actually visualize it. It is about 20,000 parts per million. So, you can actually see it, and as it is getting that deformed, loosening and flexing, it is able to change the position of the system. And what happens side by side, I should have had run this, that the tip, if you look at it, what is happening to the tip? That tip, I had given a difficult task, something with an infinite radius of curvature to suddenly with a finite radius of curvature. So, by changing these muscle positions, it is actually following this particular pattern. Okay. So, and that is what is the challenge for a trajectory tracking system. And this is in ASME design, we have reported it, and with a plus minus 200 micron accuracy currently, you can actually do this in any two dimensional trajectory system. Okay. So, coming back, we can also use the same material as a sensor, and this challenge came to me because of a GM, General Motors challenge, that they have to have a steering wheel in which they do not want to use any mechanism for the typical the what you call the direction change. Okay. There is a auto shut off mechanism. If you drive a car, you will see, you put a right indicator on, and then once the turn is over, it goes back to the neutral location, but that needs a mechanism, and that mechanism they do not have space. It was a new development of an automobile. So, they wanted a very low space solution, and what we have done is we have used this same shape memory alloy based system, but this time as a sensor, because you have to sense the change of angle. So, here as you can see that you have a disc in which you have a combination of conductive layer and non-conductive layers, okay? And you have two styluses there, and you know the angle between these, each one of them. So, whenever this rotation is happening, it is actually going from a conductive to a non-conductive layer, and as it is going, current will be passed to A or B depending on whether it is a conductive layer or a non-conductive layer, and as the current is passed, there are 2 micro switches which are sequentially switched on and switched off, and as a result you will get this signal. By actually taking the difference between the 2 signal, you know what is the angle you have rotated, what is the kind of rotational velocity, acceleration, everything you can get through these 2 micro switch operation. So, that is how you can use SMA as a sensor also. We have also used SMA for actually 2-phase flows, right. Like in this particular case, there is this pipeline where the SMA wire is there inside and the flow is happening. Now, SMA wire changes its not only modulus of elasticity, but also its resistance. So, hence as the 2 flow phase happens, some part of the flow will be more conductive to the heat, and there can be air bubbles, for example. So, hence the resistance of the system flip flops as the bubbles actually pass through it. So, by looking at that how the resistance is changing, you can say what is the speed at which a air bubble is passing through the system. So, you can use it also as a sensor. There is a mixing of sensing and actuation, and that I have used it in terms of an antenna system. As you can see here, that this is a kind of a space antenna, and it is a paraboloid space antenna with a gooseneck. Now, the challenge is that this antenna shape is to be controlled in such a manner that you can use the same antenna for various country, maybe morning for India, afternoon for Singapore, and then evening for South Africa, the same antenna. That means, you do not need 3 satellite, only 1 satellite can do all the 3 things. How to do it? Well, you need to change this shape of the antenna depending on the country you are actually transmitting the signal. So, to do that, I have used here a compact system of shape memory alloy based springs, which actually locks and unlocks it at various locations, and thus it can change the position of the system. Now, finally, I will come to the final topic of self healing, how you can do using smart materials. This actually got initiated because of some of the catastrophic accidents that took place in unmanned aerial vehicles. One of them is actually this Google Solara system, which crashed due to the large wing deformation. Apparently, this happened when there is a sudden change in speed and the wing structure deformed, and once it deformed, the aerodynamic coupling happened. So, it has a drastic turn, and it was unable to, they were unable to control the system. So, a small change, if you could have made rectification at that stage, this deformation might not have taken place, and that beautiful automated vehicle can be actually saved. The same thing happened with another crash of an aircraft, where a small pit has actually initiated the crash of the whole system. Now, that means you should have a system which should automatically heal itself. Well, how do biologically it happens? The way it happens when your bone cracks. Today, we go to doctors, right, but suppose a place where there is no doctor there. Well, our body to a good extent has the capacity to heal. Of course, it will not be the exact shape, that is why a doctor is needed to hold it at a perfect shape, so that you retain the exact structure, but to a good extent you can make it functionally ready. And the way it does is that it first creates something which is called a hematoma formation in the bone, and then from this hematoma the fibrillous cartilaginous things that are actually that come out, and then there they start to deposit calciums, and finally the bone has healed. And this whole thing has been actually designed by a famous Indian scientist whose name is Ramchandran, who has actually obtained the first collagen structure simultaneously at the time when DNA was discovered. So, we have a tradition of understanding what is this. Now, that is for the bone. For the plants also, they have a very interesting thing, which is called the change of role of a cell through de-differentiation, and these particular cells are called pluripotent cells. So, that they change their role, like in this case there is a cut in the leaf. So, all these adjoining layers, they will change their role from photosynthetic role to actually it become pluripotent, and it actually changes itself in terms of migrating from one point to the other through a quick growth process, and through cells like hypocotyls, and then it actually joins itself. Looking at these two examples, people have developed this idea of some kind of a polymeric system which has some microcapsules and some catalysts, and then if there is a crack, then these capsules get actually broken and the catalysts start to work with it, and it can actually repair the crack. That is the idea in this particular case. And also people have worked on supramolecular system, and the supramolecular polymers are actually having non-covalent bonds, so that you can dynamically change it, and we have used such polymers in terms of bonding for different types of healing process. People have also used vascular networks. So, here what happens is that you develop a network through the network a chemical reagent, like this. In this particular case, you have a channel, 3D microchannels, through which you are getting this MDI, and whenever there is a enough amount of actually moisture, then this whole process stops. So, that means it actually relies on the fact that if there is some moisture present outside, then that means there is a damage. So, the healing has to start, and once that moisture level reduces, that means the damage is over. So, it immediately stops. This type of healing systems are called extrinsic self healing systems, intrinsic self healing systems, and the problem with such system is that they are generally passive system, and they are generally an open loop process. So, you cannot really control the healing process, and there is really no controllable mechanism to terminate the process. So, the healing may happen for quite some time beyond a certain issue. You might have seen this Terminator movie, right? Did you see that? Okay. So, how this whole system changes, and then once again it comes back. Now, when it comes back to the original shape, it actually comes back to the perfect shape in which it was there. So, that means the healing happens 100% to the original shape itself. Now, that is the challenge that does not happen in many of these systems. So, to remove that, we have actually gone for a better system, which is an extrinsic healing system, and towards that direction we have developed a new solid self healing system, which is actually based on the PVDF, the same PVDF which is earlier used for sensing, along with a HFP, the hexafluoropolypropylene. So, it is a PVDF HFP based system, and the advantage of this system is that it can actually attract metallic ions. So, we have a storage of metallic ions. Whenever we see that there is a crack, the PVDF senses the crack because there is a change in strain, then it attracts the ions, the metallic ions, and because it is the structure of PVDF HFP has actually lot of fluorines available with it. So, in this case it is actually attracting lot of copper ions, and then using these copper ions it is healing the process. The advantage of this system is I have developed an experimental setup to show that you can control the healing process in a perfect manner. You can go back to the perfect shape. So, you need several type of control strategies, some adaptive control and some estimation you need in a inner and outer loop. I will not go into the details in this, but by using this type of a system you can actually heal it. So, in the healing, of course, our challenge is that how to have a good strength of healing, but to keep the healing process reversible. That means, you can go up to a particular extent, stop it and decide whether it is good enough healing or not, and how to integrate it with a predictive prognosis process, how to supply the healing material, how to identify the critical healing regions. These are all our challenges. Now, I would like to summarize the whole thing, that in terms of the application of smart materials, then our first objective is how to have a higher IQ, in the sense how do we increase the responsiveness of a system, how can we make a very fast system, because there are many dynamic systems which works in millisecond or microsecond range. So, to increase the speed of the actuator or the sensor is a demand that we work on. The other point is how to increase the functionality. It is self sensing, because direct and reverse effect both are there. Can you integrate self healing? I have shown you one example. Can you make it energy harvesting or energy scavenging, and sometimes autophagus also. That means, if your robot is caught by the enemy, can it self destruct? So, that is the autophagus system. And of course, it is to be integrated with some of the things in nanotechnology to go in a micro scale and to make it more varied, complex or intelligent, but that is something else I would not touch in this issue. So, I think this is broadly where the research is going on towards the development of advanced smart materials. This is where I will close today's talk. Thank you. Yeah, if there is any question, please.
SMA for 4D printing.
Tell me.
Can you use SMA for 4D printing? Can you use SMA
For?
4D printing.
For printing.
4D, 4-dimensional printing.
4 dimension means you have to explain it to me.
Like X, Y, Z and time.
Yeah, you can.
Use, right?
Yeah, you can use it, definitely. Now, you want to use it as in terms of actuator control, right?
Yeah.
So, some 3-dimensional and also with respect to time. You can do that. Yeah. Is there any other issue that you want, or otherwise what I would suggest is that you visit my website and see, and if you have any clarifications or anything, you just contact me over email. Okay? Thank you.